In this video, we're going to do an example where we count the number of ways to rearrange indistinguishable marbles. So the example says, suppose we have 3 red, 2 yellow, 5 green, and 4 black marbles. And marbles of the same color are indistinguishable. And that means we just can't tell them apart. How many ways are there to arrange them in a line? So to get started, let's label our marbles as letters. And because we're going to have multiple marbles that are the same color, let's initially label them with subscripts. Okay, so we have 3 red marbles, so I'm just going to write R1 for the first red marble, R2 for the second, R3 for the third, and then 2 yellows, so I'll write Y1 for the first, Y2 for the second. Then we switch to green. There's 5 of those, so G1, G2, G3, G4, and G5. And then finally 4 black marbles, so I'll do B1, B2, B3, and B4. So we have all of these marbles here. And in total, if we add up 3 plus 2 plus 5 plus 4, we get there are 14 total marbles. So at first glance, because we have 14 objects, we notice that there's 14 factorial ways to permute them, to rearrange these. But as we've seen before, because we have these objects that are identical, and this happened in examples where we're rearranging the letters in a word, and there were multiple letters that were the same. If we rearrange, say, for example, all the reds individually, it doesn't change the overall kind of like order and what it looks like. So 14 factorial is going to over-account for that region. It over-accounts since, for example, rearranging the reds looks the same. And then we need to think about, okay, how many ways are there to rearrange the reds individually? Well, there's 3 factorial ways to permute the reds once all the marbles have been placed. There's 3 factorial ways to permute the reds in their spots. So to fix this, we are going to divide by 3 factorial, because right now we're counting these arrangements too many times. We're off by a factor of 3 factorial. So we're going to divide by 3 factorial to fix the reds specifically. And we're also going to have to divide by stuff to fix the other colors. So let's write that down next. So similarly, we will divide by 2 factorial to fix the yellows, because there were 2 yellows, and there's going to be 2 factorial ways to permute them that look identical. By 5 factorial to fix the greens, because there's 5 factorial ways to permute the 5 green marbles we have. And divide by 4 factorial to fix the black marbles and how much they will overcount by. So this will give us our final answer when we finish dividing, which is, initially we said 14 factorial, but then we're dividing by 3 factorial, that was to fix the reds, and then 2 factorial for the yellows, 5 factorial for the greens, and then 4 factorial for the black marbles. And all this stuff on the denominator was stuff we put to fix the overcounting. Okay, so I'm going to put a smiley face there. And if we work out what this is, this gives us 2,522,520. And that's our answer. So I'm going to box this whole thing, because if a question like this didn't ask us to simplify our answer, we could leave it in this fraction form in terms of factorials. But if it did say we can use a calculator to evaluate it, we want to put this in this final form as like around 2.5 million or so. So in terms of our goals for this section, we finished our first goal. Over the last 2 videos, we've done some more challenging counting problems that involved permutations, combinations, and multiple techniques such as adding, multiplying, and adjusting for overcounting. In the next video, we'll talk about how to use complements to count certain objects and to recognize when we might want to use complements for counting purposes.